Okay, so thank you everybody. This is an exciting session to be involved in, and I thank you for inviting me to speak about something that I'm very passionate about. So I think you'll get the idea of this talk just from the title of it, but I want to show these two pictures right here as a kind of motivator to what I'm going to be speaking about. You know, we all have this romantic image of an astronaut on Mars or the moon dangling off a rope and with a pickaxe and taking samples. But really, this would be, in my opinion, a great job for a tethered robot for a number of reasons, including the ability to leverage surface power, of course, keeping humans safe, and the ability to carry a suite of instruments with different modes of articulation than a human would otherwise be able to do. So I hope you get that takeaway from this, and I want the audience to potentially embrace tethered robots for exploring extreme planetary environments in the missions that you consider in the future. So, you know, tethering is not new. On Earth, power and communication tethers reign supreme for efficiency, speed, and reliability. So whether that is crossing continents with an enormous power grid system that pretty much connects the world, going undersea, whether it's buried sea cables that join the continents in terms of communication, or exploring the depths of the ocean, looking for shipwrecks or whatever you happen to be looking for in your robotic endeavors. And then underground, so anywhere there's a resource limited environment, tethers are a good option, even for big mining trucks like that. And then of course, indoors, we are drowning in wires. And you know, we do live in a wireless age, but in reality, you know, we're truly wired, and it's truly the most reliable and quickest form of communication still to this day. So my argument is that this is not going to change as we start to settle different planets and moons in our solar system. So whether it's building a base on the moon or Mars, we're going to need access to power. So that means power lines. In the top left image, you'll see a kilowatt reactor. This is a concept from NASA Glenn that can produce from kilowatt power to 10 kilowatt power, maybe even more in an array. But you're going to need tethers to transfer that power a safe distance, because these are reactors, so we can't have astronauts next to them. The image on the right, top right, is from SpaceX. This is the kind of colony that they'd like to build. You can imagine that there's going to be tethers involved with that. I mean, call them cables, call them tethers, whatever you want, they're going to be there. So the idea is, you know, robots laying these out versus humans. And, you know, of course, exploring inside of resource limited environments like permanently shadowed craters, where we want to look for volatiles in the surface so we can have astronauts be able to drink water or to use it as fuel for wayward missions into Mars. So a lot of people in the room might not be aware that there are already many tethered mission concepts underway. Luckily, if you were all in the talk yesterday, you probably heard Dr. Laura Kerber from JPL speak about Moondiver. This is an excellent mission highlighting the capabilities of tethers. So this is a large moon pit that's roughly 100 meters across and 100 meters down that we'd like to send a tethered robot. I'll just quickly go through some of the other concepts. The prime concept is a mission to Europa, potentially having the longest tether that I've ever heard about. So it's going to probe into the ice using a melt probe technique, and it's going to potentially go 40 kilometers into the ice. So this is definitely a resource limited environment. We cannot easily communicate to the ice, so we'd like to bring a tether along. Eels, just below that, is a snake-like robot for Enceladus. Far side in the top right is a interesting concept for a tethered dipole array, where the tether itself becomes an instrument and is driven out a distance covering roughly a 12-kilometer diameter area to deploy an enormous array of dipoles. And then, of course, Mars exploration into these RSL features, which we think of might be salty brines on the surface activating seasonally. And then you could think of constructing enormous structures like on the bottom with the Lunar Crater Radio Telescope that you may have seen in the news lately. Now, I'm going to make a controversial statement to some, but I really think this holds true. All untethered robots are at some time tethered. So I'm always saying put a tether on it, because tethers are part of our world anyway. These are some great pictures that show what would otherwise be untethered robots rather tethered. So, and I love the picture in the top left because Mars 2020, it's off exploring Mars, but the one that we have at JPL, it's always tethered. There's two tethers, in fact. There's a power data tether, and then there's like a cryo tether. So essentially they're pumping liquid nitrogen into the system to cool the system because it was never designed for the California heat. And then even Mars Heli, a flying helicopter, uses tethers in its tests. Now, any good roboticist knows that you detach all these ugly looking cables and cords prior to making this cool video you submit to potentially the IROS conference or ICRA, but I say embrace it. So this is not the first time people have thought about planetary tethers. In fact, the Apollo astronauts deployed tethers on the moon with their surface experiments package back in the 70s. They had some interesting tethers that were used to deploy a suite of instruments, all communicating to a central hub. The Mars 2020 and Curiosity robot that landed around 2012 actually used a tether during the descent phase. And then one of my favorite tethers that I hope gets to see action in the near future is the InSight mole tether. So the problem of fortunately for me, was not the tether as to why this mole was not digging into the surface, but rather the strange properties at the surface of Mars. They were able to bury the mole, so I'm hopeful that they'll get that thing going soon. But that tether is interesting because it's instrumented with thermocouples along its length, so it's going to tell you something about the heat flow of Mars. But a lot of people are scared of tethers. In fact, if you say tether at NASA, you get a lot of strange looks in the room because they did a lot of work in the 90s deploying a lot of electrodynamics experiments in space. And they saw a good amount of failures, including the one shown where a metal shaving during construction of the tether shorted the tether while in orbit and caused the loss of a probe from the space shuttle. So you can imagine having a dangling tether from the space shuttle is not a very good idea. So you get the idea why they might be scared. And there are many other reasons to be scared. Tethers are problematic. They're prone to fail in challenging environments. So you have to think about this when you design a tether. This non-exhaustive list are just some of the pitfalls of using a tether, but I believe that you can design around these things. Particularly, especially if you're thinking about loading your tether using it as a climbing rope, that's a pretty challenging environment. And then, of course, the environment matters a lot. So we're talking about the moon a lot lately. Well, the regolith there is made of glassy particles. And the astronauts, one of my favorite pictures is in the lower right. He's absolutely covered in regolith. It embeds in the fibers. When they did analysis of the suits later on, they found that this regolith was just tearing apart the suit, even for just a few hours on the surface of the moon. So our solution at JPL has been to recently develop a very robust planetary tether. It's made of high-strength fibers and wound wires and an extruded abrasion jacket. And the neat thing about this is that we've made a tether that's 5 millimeters in diameter, sometimes less, depending on the wire configuration, that can support up to 1,000 pounds. And it's obviously just 8 wires there, and has a very low mass profile. And we're working now on next gen power capabilities that will allow us to transfer hundreds, if not thousands of watts across kilometer distances using high voltage power supplies for space applications. And then if you want to use optical fiber, you can get up to gigabits per second bandwidth through kilometer distances, up to 40 kilometers. So there's just many options here. And we've even looked at doing planetary testing. So, you know, in preparation for this moon diver mission that you hopefully heard about yesterday from Laura, we exposed these tethers, we designed this tether and exposed it to some pretty crazy tests. So in fact, we did rub it with rocks and regolith back and forth. We exposed it to knife edge bends, looking at the continuity of the wires, and we load those tethers up to the load that they would see on the moon and see if they break. We've driven them in the field. We've even exposed them to UV, which is much worse in space because there's no atmosphere on the moon to protect from the full spectrum UV. But the point here is that we've done a lot of tests, and we are rather confident that this is a reasonable solution for supporting a rover exploring extreme terrain. So since we are mostly roboticists in the room, I want to just highlight some robotic work in terms of autonomy that we've done for tethered robots, including myself and some colleagues at JPL. So I've been working on tethered robots for nearly 7 years. I was a PhD student at the University of Toronto, where I worked on my first tethered robot called T-Rex. And I started to think about let's get around some of the problems that people see with tethered robots. And the number one thing that everyone always says is, what happens if they get tangled? And tangles happen when you drive through complicated environments and you add anchor points along the way. So these anchor points are just contacts with the terrain. And then in order to safely return to your starting destination, assuming it's a two-way mission, the one-way missions are a lot easier, by the way, because you don't care about these. But if you want to come back, you have to bookkeep where these things were. So I want to highlight 2 bits of work. One that I did in my PhD, and then one recently that was a part of this conference, actually, by a colleague of mine, Michael Payton. We've looked at tether slam algorithms. So I developed in my PhD a way to localize anchor points driving through complicated environments using non-visual information. So just using tether information, bearing, tether length, those types of things, and wheel odometry to localize anchors, and then run a batch estimation to kind of relax that map and put it into a configuration that most closely matches the ground truth. There's some papers there if you want to check that work out. And then I would love for you all to check out this paper by Michael Payton. It's at IROS this year. It's about tether-aware planning, and it uses a sample-based planner similar to the one that Will spoke about to kind of think about the environment and the way the tether lays in the environment, and then plan for a tethered robot. So it's a little bit different than planning for a regular robot because you have this external force dynamic coming from the tether. So this means that in certain configurations, depending on where the tether is going, you're more prone to slip. So if the tether is pulling you down a slope, that's not very good. So we want to plan paths that allow us to reach reasonable goals on complicated terrain. And the complicated terrain could be on top of a boulder. So there's no really limit to the way this rover can drive, but we like to think that we would be able to get back in order to detach our tether. So that just highlights some of the quickly some of the work we've done. There's a number of papers out there. I've written a few of them, and then Mike has written a few, or we'll write more probably in the coming future. So look forward to that. And it's a fun field to work in because there's just a lot of problems to solve. So I highly recommend it to if there's any PhD students out there that want to solve a fun problem. Okay, so you probably heard about Moon Diver yesterday, but I want to maybe show a video that you didn't see that highlights the capability of a certain rover I've been working on a while called Axel. It's this 2-wheeled tail dragger, and it has the ability to deploy instruments on nearly vertical surfaces and then drive down them as well, which is a very unique capability. And you might ask, oh, if you're on Mars, why not use a UAV? Well, UAVs are fine, but they're not going to give you the payload capacity, and they're not going to give you the long integration times from taking a measurement. It's as simple as that. So tethers allow you to sit in places for a very long time. You can recharge for days. It wouldn't matter. You can just hang there. That means you can have longer missions. You can do more exacting science. They're incredibly helpful. Now, I mentioned before constructing a civilization on the moon, or building a base, building infrastructure, leveraging power sources from nuclear reactors on the surface of the moon and Mars. Now, this is work that shows, in a kind of a crude fashion, an Axel rover driving off a fake moon lander. So this is not on the moon, unlike the video would be made to show. But this is a 1-to-1 scale size of that reactor. And that lander is a 1-to-1 scale of a very small lunar lander intended for the Phoenix mission. So you get a sense for the scale there. And that robot is 100 kilos. And its wheelbase is roughly 1.5 meters across. But the idea is that a tethered robot doesn't need egress mechanisms on a lander. It doesn't need a davit platform. It can actually just drive off. And the tether, even over that knife edge bend, is fine. We've done these tests. And then we can carry a large capacity of tether, in this case 300 meters, but it really depends on how you design your spool and how thick the tether is. And the idea is that with a nuclear reactor on the surface, we don't want to be next to that. Even electronics don't want to be next to that when you flip it on, because it's emitting. So the idea is that we drive some distance away. In this case, we didn't drive very far because we didn't have that much space, but another surface asset, let's say the Athena rover, that is another interesting rover at JPL, can drive up to it, and let's say its batteries are running low. Well, a surface axle deploying a power tether as kind of a utility can allow other rovers to come up and charge on it. You could also think of driving this to your human settlement, where it's a safe distance now, and you basically power parts of the settlement. And 10 kilowatts is a lot of power, especially on the moon. It's orders of magnitude more than we typically use for robotic missions. And then once that rover is charged up, it could drive away. And then Axel can sit there and wait for someone else, or it could go off and explore, because it's an extreme terrain robot in of itself. It could deploy instruments from those same payload bays that you just saw open up. So that kind of highlights that work a bit. And then I want to show something that I'm really excited about. So the question often comes, like, how do you anchor this robot if you're like on Mars and you're not close to where you need to go because the tether is a finite length? Well, to me, the answer is to develop a robot that can anchor itself. So this is DoAxle. It's a very capable articulated steering vehicle inspired by the Zoe robot, which I believe Dave Wettergreen is speaking next, and they developed that robot, so thank you to them. But this is a transforming robot that can sit and stand, and when it sits, it actually becomes an anchor for the tethered robot down below. You might have seen this. This was a part of a press release by JPL in the last 2 weeks, and hopefully you did see that. But if you didn't, I'm glad you could see it now. Go watch the high-res version online. I'm sure it's choppy over Zoom. Anyway, we can navigate down slopes. And the idea here is to look at Mars applications where we're looking for water on the surface of Mars, briny flows on crater walls. And we can deploy a suite of instruments that look at briny features and determine if there's, the water bands are within the reflectance, given, let's say, an IR spectrometer or other instruments. And then we can deploy these instruments on the surface. But on Mars, we have this time delay, so we're going to have to think about autonomy more. And this is where Mike Payton's work comes in. And this is, we're a big team, and he's developed this tether-aware planner, and this is some of our onboard autonomy running and choosing its own path. So Axel is driving itself, thinking about its tether, thinking about the obstacles in the environment, what it can and cannot do, and then navigating down. So in this scenario, we tell it to go some distance, and then it would do that, and then we would take measurements and think about what those measurements mean. And then most importantly, at the end of the day, let's say you've explored a steep area that maybe is not fruitful and you need to move somewhere else. You can return this axle rover back to its dock. It will retract into its dock. So there you see it doing that. And then finally, it will stand up and then drive along to visit another target. So I hope this talk has shown you that tethered robots are indeed interesting and something you should consider in your future and for future exploration. And I hope you all embrace the idea of the tether. So with that, I'll say thank you and then ask for any questions.